We've been evaluating definite integrals by looking for any antiderivative and then evaluating the antiderivative at places. And the authority for doing that so far has been because I said it was right. But there's actually a much deeper authority. This is known as the fundamental theorem of calculus. Anything called fundamental must be important. And it's what ties together the two branches, the differential and the integral calculus. And it can be stated just like this. If f of x is a function and capital F of x is any antiderivative of f of x, then the definite integral from a to b, lowercase f of x dx, is equal to that antiderivative function evaluated at b minus the antiderivative function evaluated at a. And that is a striking result. It makes taking of definite integrals, finding areas and other applications, about as easy as finding an antiderivative, which we became fairly facile at, and then evaluating it two places. There's another longer but also theoretical development of the definite integral that students in the non-applied calculus would learn. So if this is a function f of x, and if this is a left endpoint a, and this is a right endpoint b, then we learn that the definite integral from a to b, f of x dx, is the area under this curve between a and b and above the horizontal axis. And so we can calculate the integral by looking at a series of little rectangles here, calculating their area and adding them up. Now, how do we get the area? Well, it's always width times the height for a rectangle. And the width is pretty easy. We just take the a to b and we divide it into a certain number of little segments, and this choice is up to us, and so not a problem. What about the height, though? Do we take the height at the left end point, or at the right end point, or somewhere in the middle? Or do we get the area of this little cell by putting a roof on it, a straight line roof, in which case it becomes a trapezoid? Or do we try to fit a parabola on top of it? A parabola might better fit this curve, f of x. So lots of different ways that we could do that. Whichever way we do it, we come up with a figure for the area, and then another area, and we continue until we've calculated the area under the curve. Now, we know that's an approximation. If we would divide these little rectangles in two, we'd have twice as many of the rectangles, but because we'd have a better idea of what the actual height of these rectangles was, we'd have a better approximation of the area. And so in the end, as so often the case in mathematics, we wind up taking a limit as the number of rectangles increases without bounds. So I'm going to say n for number of increases, number of integrals increase without bounds goes to infinity of the area of rectangles. and so I don't want to be too precise about that. But that would give me the really good approximation of the area underneath this curve, and that's what we would call f of x. How much simpler it is to use the fundamental theorem of calculus and to define the definite integral as two antiderivatives evaluated at the lower and at the upper limits and then take their difference. So that's what you need to know about the fundamental theorem of calculus.